So if this one's not that much better than Euler's in general, and it requires that much more computation, why are we doing it? Well, we're going to get at that question now. So should both slopes be weighted equally? Should they both be weighted out of 1/2? Now the reason that we say weighted with 1/2 is because here if you distribute the 1/2 in, K1 and K2 will both get weights of 1/2. We call those weights. Now we arbitrarily chose the slope at the current point and the hypothetical slope at the Euler's method next point, and we chose to weight both of them equally in the average. Note that you could always weight one term by, say, 1/6 and the other by 5/6. So when you take 1/6 of something and 5/6 of something else, you still get a whole, but you're placing 5 times more weight on the second term, or vice versa. Improved Euler's method is actually Runge-Kutta 2. What this means is that we will approximate the next y value by using a Taylor series approximation. So it seemed like we kind of arbitrarily picked the weights and we arbitrarily picked which slopes to use. Hopefully there was some intuition behind that, hey, yeah, let's average things together and let's use a slope at the beginning of the interval and at the end of the interval. So I think there's some intuition in that. But we haven't answered why we weight both of them equally and why we should be using those two particular different slopes. So we're going to be using what's called a Taylor series approximation. And I recommend this video highly. It's 22 minutes long, and you're gonna find some valuable information there about what Taylor series is. I'll describe it here in a nutshell. So in a nutshell, what the Taylor series does is it's a way to take a complex function and approximate its shape in a neighborhood, using only polynomials, in fact. So for example, for small angles, cosine of x, which is called a transcendental function, it's actually really hard to get calculators to graph these functions, believe it or not. And you can actually approximate cosine of x for a neighborhood, meaning for just values very, very close to x equals 0, by using the function 1 minus x squared over 2. And that's a first order or second order Taylor series expansion. So what you notice is that the red graph here is cosine of x, and the blue graph is 1 minus x squared over 2. And you can see that from about here to about here, we have that blue graph provides a really good approximation to cosine. So as long as your angle is, theta is between somewhere, I don't know, negative 0.8 less than or equal to theta less than or equal to 0.8, or maybe not theta, but x, we use x instead, then for x is between these values, the blue function does a really, really good job of approximating the values on the red curve. So, but it's a much easier function to work with. So if you know you're going to be working with small angles, then you could replace the function cosine x with 1 minus x squared over 2. The reason we like polynomials is they're easier to differentiate. Quadratics have nice formulas like quadratic formula. Polynomials are just in general much easier to work with. So 1 minus x squared is a second order Taylor series expansion, or TS2 if you will, to cosine of x. We can increase the order and find an even better fit. This is called a fourth order Taylor series expansion, and now you see that so this is second, this is fourth, and you can see that the green curve expands the domain. You can actually see that it's a really good approximation from there to there, whereas the blue curve is only a really good approximation from about there to there, as we saw in that previous illustration. So increasing the order of the Taylor series basically just creates more curvature to contour the function you're working. And that's all a Taylor series expansion really is. It's creating a polynomial that basically increases and decreases more and more often as you increase the order, because if you take a quartic, it can change direction, let's see, 1, 2, 3 times. It changes direction. And so if you did a fifth order, it could change directions up to 4 times, giving that think about that function as being more pliable or more flexible. So that's kind of what a Taylor series does in a nutshell. We're not going to derive this, but again, if you watch that video, you'll see the beautiful derivation of this. But if we want to approximate a function, it doesn't have to be near x equals 0 like it was. Let's say we want to approximate it near x equals a. So, again, that if we were looking at the cosine function and we wanted to approximate it at x equals pi halves, and we wanted to find something that fits sort of this portion of the function here, then we could do that. So our a in this case would be pi halves. Okay, so you can see how this pieces together, and this just says plus dot dot dot. And the reason for that is because the only way to get these to be exactly the same is by having infinitely many terms. We're, of course, not going to keep infinitely many of them because that's no more practical than trying to use a complicated function. The more terms we keep, the more accurate the approximation, though there is a practical to complex trade-off after about the fourth order term. Now, we don't do f prime, 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 prime. We usually just say f with a 4 in parentheses, so it doesn't look like f to the fourth power. That's the fourth derivative. So you really just gain way more complexity than you do benefit after the fourth order terms. But let's just keep this really simple and say we only took the first 3 terms. So we went up to the second order derivative. Now notice that my sign here is no longer equal to, it's approximately equal to. How approximate? Well, it's going to depend on the function, depend on the point. It really just depends. So we could get a really sloppy approximation or a really good one, but this is better than none. Now, so this is an approximation to a function. The function that we want to estimate is, recall that we want to find y sub k plus 1 based on y sub k plus some delta t. I'm going to stop using delta t, I'll use h, plus h times some proverbial slope. Okay. So we want to estimate that proverbial slope to get y sub k plus 1 to be as exact as possible. Now, y sub k plus 1 doesn't look a whole lot like the notation here. So what I'm going to do is I'm going to go ahead and write y sub k plus 1. What that really means is the y value at our current value of t plus a step size. Right? So basically, this is the y value at some point. If I call this t, and t plus h is over here, what I want to do is, based upon this point, I want to estimate this next y value over there. So this y value here is y at the t coordinate t plus h. So I want to estimate this. Now, that's kind of like my f of x. That's what I want to estimate on this side. So what I'm going to do is I'm just going to say, all right, well, this is analogous to saying I want to expand y of t plus h. Now this point right here is central to the function, and so I'm going to write almost without too much justification here that this term is going to be like our y of t. F of x is the actual function. F of a is the function evaluated at the current point. So I'm going to kind of write this without a little bit of justification here because it does require some limit thinking. But x minus a, this is going to be an accurate approximation if this quantity here is infinitesimally small, and we often call that h. So 1 factorial by definition is 1 times 1, or just is equal to 1. So this will be h, x minus a, we're going to replace that right there with h. And a is our current value of t, so we'll write f prime of, sorry, not f prime, but y prime of t. And we'll do the same thing over here. Here is h, we want that to be really, really small. And 2 factorial is 2 times 1, so this will be h squared over 2. Times y prime prime of t. Now, recall that one thing that we wrote is that dy dt is a function of both t and y. So, in order to compute its second derivative, or we could say y prime equals f of ty, its second derivative will be, we've got to use the chain rule here, If you haven't taken Calculus 3 yet, this derivation may not make a whole lot of sense for this given moment. But if I want to compute the derivative of a function that depends on two inputs, which is y prime, we could use the multivariate chain rule. And we have that y prime is a function of t, and it's a function of y, and y itself is a function of t. So with each of these little chains, they're all, in order to find the rate of change of y with respect to t, in other words, to find y prime prime, I have to follow the chain all the way down and take the derivative of y prime. Remember, y prime is f of ty. So I have to take the derivative of f with respect to t. And I also have to follow the chain this way, which will take the derivative of f with respect to y, and this link here, take the derivative of y with respect to t. So this is going to be df dt plus df dy times dy dt. And you can see that, that if you cancel out the dy's here, you end up with df dt plus df dt. And what this essentially means is there are two different contributions to how y prime changes. It changes from a change in t as well as from a change in y. And so another way we could write this is y prime prime equals f sub t of t and y plus f sub y of t and y multiplied by dy dt, which is just y prime. Now even y prime can be written as f of t comma y. So I have this notation, which again, this looks very daunting because there are a lot of symbols here. We just need to remember what these are. This is the first derivative, which is just f of t comma y. Now what I'm going to do here is, so I would just establish that y double prime is f sub t, t comma y, the partial of f with respect to t, plus the partial of f with respect to y, multiplied by f of t comma y. So what I'm going to do in this form now, and we're getting closer to the solution, is I'm going to say that y of t plus h is equal to y of t plus h times y, instead of y prime of t, I'm going to use f of t comma y, and plus h squared over 2 times what y double prime is, which is this whole expression. So that's just a substitution step. And we're very, very close to actually seeing this as your next y value is your previous y value. Notice that this is the very first slope right here. This is what we call K1, or pretty close to K1. We're going to do one more thing here, and this might not be something that you're familiar with, but the multivariate Taylor series expansion is going to look like this, that if you have y of t plus h, f of t plus h, f of t plus h, comma, y plus k, that this is going to come out to f of t comma y, f of t comma y, plus now this is going to be h times f sub t with respect to t and y, plus k times f sub y with respect to t and y. And you notice that this is really just the same thing as the original Taylor series expansion, except it includes a term for both the t component and the y component. But this is all we really need. And I'm going to do one little trick here. The f of t plus h, if instead of having y plus k, I had y plus h times f of t comma y, if I had that in place, then all I would have to do is replace the k with this expression here, h f of t comma y. And the reason I'm going to do that is because this will allow me to make a substitution in our expansion up until this point right here. So we're trying to condense this down a little bit. And I see that what's on the right-hand side here looks similar to this, except that we're off by this extra term. So here I have k being replaced with h times, I'm going to replace k with, here's our k, right? Here's our k, and our k is really this extra plus piece. So now I'm going to replace k with h times f of t comma y, and then that still multiplies f of y comma t comma y, plus etc. This will give us an exact expansion for this multivariable function. So this is the same thing except for multivariable functions where you're in 3 dimensions and you want to approximate a 3-dimensional surface instead of a 2-dimensional curve. So you can see that from up here that what we have with respect to these terms here looks pretty similar to what we have down here, which means that I should be able to replace that. And I should have been using approximately equal to all the way along because we are approximating this with only the second order term. So if I factored out an h from here and I factored out an h from here, what this would give me is y of t plus h is approximately equal to y of t plus h times quantity f of t comma y plus here I'll just have h over 2 times f of t, so distribute, well, we factored out an h, so we don't have h squared anymore, but I have h over 2, which will distribute f sub t of t comma y, plus h over 2 times f sub y of t comma y, times f of t comma y. And what we should see from this is that this again resembles very closely what we have right here, with the exception of that factor of 2. And I'm going to argue that if you rearrange this a little bit more, you'll have y of t plus h is approximately equal to y of t plus h over 2 times f of t comma y plus, and this will be h over 2 times f of t plus h, y plus h of f of t comma y. And so what we're getting at here is that this is approximately equal to y over t, y of t. Now if I factor out an h over 2 from both of these two terms, what I have left inside of here is, notice that this is just k1. That's what we've called k1, and this piece here, this is what we've called k2. And now you can see that what we have as the second order Taylor series expansion, the same answer is obtained, though this answer is one that is derived mathematically for the best weighting of the two slopes. This answers our two bolded questions from above. So I realize there's a lot going on here, and you don't necessarily have to be able to rederive this, but at least seeing how we kind of do these types of things might be beneficial to seeing. So our intuition was right. Let's use the beginning and end slope, and let's average them together, giving them equal weights.